Hello! In this third video of the series, we will learn about acceleration vectors. So far, we have considered the motion of an object. When an object is in motion, not only does its position change, but generally its velocity can also change. Just as we consider the average velocity from the displacement vector, we can consider the amount of change of the velocity per unit of time. This is called the average acceleration. This figure shows the motion of an object along a trajectory. Suppose that at time t, the object has a velocity that corresponds to this arrow here, and that after a small time interval, delta t, the object's velocity has changed like this. Taking the starting point of these two vectors at the same position, the amount of change in the velocity vector is the velocity vector at t plus delta t minus the velocity vector at time t, which is given by this red arrow here. Then, dividing by the time taken for this change, delta t, we get the average acceleration. Just as we define the velocity vector from the change in the position vector, that is, the displacement vector, we can now define the acceleration vector from the change in the velocity vector. This is the definition of the acceleration vector. Acceleration is usually expressed by the letter a. In the limit of a small time interval delta t, we can define the instantaneous acceleration. Just as the velocity vector is given by the time derivative of the position vector, the acceleration vector is given by the derivative of the velocity vector with respect to time. And since the velocity vector is the derivative of the position vector with respect to time, the acceleration vector can be expressed as the second-order derivative of the position vector with respect to time. Now, I would like to make some comments about acceleration. First, acceleration is the change in the velocity vector per unit of time. The standard unit of acceleration is the standard unit of length, the meter, divided twice by the standard unit of time, the second. We call it meters per second per second. This can be understood as a change in the velocity divided by the time it took for its change. So we divide the unit of velocity, which has standard units of meter per second, by the unit of time, second. Acceleration is also a vector, so it has direction and magnitude. And since the acceleration vector represents the amount of change in the velocity vector, if the amount of change in the velocity vector is zero, that is, if the velocity vector is always constant, then the acceleration is zero. On the other hand, if the velocity vector changes in a time-dependent manner, the acceleration is generally non-zero. The word acceleration tends to give the impression that when the acceleration is non-zero, the object is rapidly increasing its velocity. However, acceleration is present whenever there is a change in the velocity. So, even when an object is decelerating, we still say it is accelerating. I would like to draw your attention to this point. Unlike position and speed, which are often visually perceptible, acceleration is invisible. Therefore, you may often find it difficult to understand it intuitively. When you feel that acceleration is difficult to understand, it is a good idea to go back to its definition and think about how the velocity vector is changing. Now, I would like to show you one concrete example. Let us consider the vertical motion of an elevator and take the x-axis in the vertical direction. The height of the elevator is represented by the x-coordinate xt. In other words, the elevator's position coordinate is written as xt, the velocity component in the x direction is written as vxt, and the x component of the acceleration is written as axt. In this case, the velocity and acceleration may be positive or negative depending on the elevator's motion. For example, consider an elevator that has just begun to move upwards, increasing its velocity towards the floor above. Since the elevator is ascending, it has a positive-oriented x component of the velocity. Therefore, Vx is positive. Also, if the velocity in the x direction starts out slow, and increases over time, the difference between the two vectors is a vector in the positive direction of x. So the acceleration is also a vector in the positive direction of x. Next, consider the situation where the elevator is ascending and then decelerating to a stop. In this case, the elevator is also ascending, so the x component of the velocity is still positive. On the other hand, what about acceleration? The elevator was going up at a high speed at first, but just before it stopped, it slowed down. The velocity vector has shrunk like this. If we think of the amount of change between these two vectors, subtracting this vector from this one, we get a vector pointing downwards. This means that the component of the acceleration in the x direction is negative. Now let us consider a situation in which the elevator on the upper floor begins to descend, increasing its speed towards the lower floor. Now the elevator is moving in the negative direction of x, so the x component of the velocity is negative. What will happen to the acceleration? The elevator started with a small velocity, then increased it gradually. So the magnitude of the velocity vector also increased. The difference between these two velocity vectors is in the negative direction of x. This means that the acceleration at this time is negative. Next, let us consider the situation where the elevator is going down, decelerating to a final stop. It is still moving in the negative direction of x, so the x component of the velocity is negative. Again, we see the change in the velocity to understand the acceleration. The elevator started out with a large velocity in the negative direction of x and decreased gradually. If we consider the difference between these two vectors, we see that the amount of change in the velocity vector is oriented in the positive direction of x. In other words, the acceleration is positive. So when considering the direction of the acceleration, it is better to focus on the change in the direction of the velocity vector. In this video, we learned about acceleration vectors. Thank you for watching and see you in the next one.